Afternoon, everyone. So today we will have a new version of the supergroup meeting, and this time we were again the same as the last time. We make our meeting become more international, and in this time we will have more non-Chinese speaking people join in. So we hope people enjoy this very good two talks we present today. And okay, then we will begin the first talk, which were given by Dr. Georg Mensah from this Dive Solution Germany, and he will present the topic on a complex material in SPH. Then George, then please have your presentation.
Yeah, thanks for having me. Let me share my screen. You see it?
Yes.
Yes, yes.
Okay. So, yeah. Hello, everyone. My name is Georg Mensah. I'm working for Dive Solutions. We are a commercial provider of SPH software. We offer our services in the cloud. And therefore, we have a keen interest in industrial research in the topic. And when I was asked for a possible topic for a talk like this, I first thought, like, okay, what is it that I can show? And then we early came to the conclusion, maybe what we internally call complex materials. And this is maybe a fun story because at our company, we have this loose definition of what a complex material is. I will explain it in a second. And if I say like we, then this is me and my about 30 colleagues, but especially Theodor Hennings and Tobias Vibranitz, who are working in the core development. They are algorithm developers. Theodor is an excellent student currently joining us for his bachelor thesis, and Tobias is the head of our development team. And I would like to draw your attention to the image here, and I won't reveal what you see there. Think about it, like the last slide in 20 minutes, we'll come back to that. Why is this a complex material? What makes it complex? So what is a complex material? At Dive, we have a very simple definition. We say a complex material is a fluid characterized by surface tension, thermal properties, non-Newtonian behavior, and interactions thereof. And the reason why we came to that conclusion is, as we work in industrial engineering, we are often faced with odd fluids, let's say. When you graduate from university, you are used to water, you are used to air, maybe oil, and then you think you've seen it all. And then you work in the industry and people ask you, hey, can you simulate chocolate flow? Can you do oil splashing correctly? What about ketchup? And soon you realize, oh, these materials come with properties that are not so easy to model. And at the same time, as an industrial provider, you need to offer a model to be commercially successful, because people are interested in what's happening in the real world and not just academic examples. And in the next 20 minutes, I will give you a few examples of like what we developed, how we develop at Dive, how we validate our models, and where we apply them in industrial applications. So very brief, as this is an SPH meeting, what is the model that we use? Basically, we solve standard Navier-Stokes equations, continuity, momentum, and we use Fourier's law as an energy equation. And our SPH approach is a weakly compressible SPH using a fifth order Pentland kernel. And I think the most interesting terms on the slides for this talk are this one. There's an extra term in the momentum equation giving rise to surface tension effect. So what you see there is sigma, the surface tension coefficient, and then the curvature of the surface. This is typically giving rise to a force that we call surface tension. Then there is, of course, the heat transfer modeled at Fourier's law. And then there's the stress tensor here in a Newtonian formulation, but you will see that I will change it to a non-Newtonian formulation to model more complex material behavior than standard Newtonian fluids. And these three aspects, they depend on one another. Temperature can change the surface tension, it can change the viscosity, and of course the fluid behavior itself is then more complex. So let's see how we do it. The first aspect is surface tension, which I would simply summarize it, make it splash. So whenever you want to do droplet formation or splashing, you need a good surface tension model. So on this slide, for instance, we run a simple test to test our surface tension model. Our surface tension model, if you're familiar with it, is a blend of the pairwise forcing and continuous surface models that you see in the SPH literature. And whenever we start developing a new feature, we think of how can we validate it. And we start with both qualitative and quantitative validations. This one is a qualitative one where we compare the formation and deformation of an impinging droplet with imagery that we found in the literature. You see that the secondary droplet formation is well captured. So this is a simple benchmark for that. We do more benchmarks. For instance, here, this is the image that you've seen in the beginning. And these tiny drops here, this is called secondary droplet formation. So basically you have droplet impact in a narrow paddle. And then as a reaction of that, you would like to see these secondary droplets form. And this is exactly what you see if you simulate. So here you see these secondary droplets. We are currently looking for a paper that is about to be published to get more quantitative reference data on that. But I'm showing this slide also to inspire you guys whenever you think like, hey, what could be a good validation case for me? Like, how can I see whether my model does what it should do? Then having a look into models or simulations like this is always a good way forward. Of course, we do also more quantitative validations. So one very simple one is Ewing's law. Ewing's law is basically telling you the filling height in a very narrow capillary. So all of you know that due to surface tension in the narrow capillary, there you see a rise of the fluid. And the height to which the fluid will rise can be computed according to a very simple equation named Ewing's law. So this is basically 2 times sigma, the surface tension coefficient, times cosine of theta. Theta is the contact angle that your fluid forms with the solid walls of the capillary. These are down here are density, gravity, and the radius of the capillary. And when you do that, you can do a simple simulation where you say like, okay, I have a capillary, I immerse it into a fluid bassin, and then I see like how the fluid is rising. And of course, due to Ewing's law, you can exactly calculate the height which you expect it to rise and compare that with what you see in your simulation. And this is a plot of a result that we computed. So basically, the black line is what you expect from Ewing's law, and this is where you see like how far it goes. So we also recommend this as a very good validation case for surface tension models because it's simple and it's relevant. You will see that there are applications which are crucially depending on capillary forces. I will show you one in a minute. Another quantitative test that you can do is droplet detachment. So basically, this is a setup that we found in an article in the Journal of Physics of Fluids. And basically what the researchers there did is they run experiments from water droplets detaching from a tap. And they came up with an equation for the minimum droplet diameter as a function of time. So this is our simulation result now. like you see it moving, and as it detaches, the minimum droplet diameter goes down to 0. And this is something that they computed. Like the black line is their fit model, and they predict in time like what is the minimum droplet diameter as compared to a reference diameter. And then you can use your simulation to compare, like, okay, is the temporal evolution similar or not until it detaches. This is another example that I would like to show you, but this is an application. So why did we delve into surface tension models? Basically, what you see here is underfilling. Underfilling is an application that you find in the electronics industry. You have a microcomputer chip which is glued to a circuit board. And one of the manufacturing processes there is that you have to put the adhesive below the chip in between the solder joints. And this is solely driven by surface tension effects. So this is something that we see in our daily work, that people approach us, like chip manufacturers, and say like, hey, can you simulate that? And then we say like, yeah, okay, we have a surface tension model, we can do that. Basically, what you see is how the adhesive front is moving under the chip. And I can tell you, like, these people are quite happy with the results that we presented to them. Next is the thermal aspect. As I said, like a complex material also has a complex thermal behavior. Our model is not representing any radiation, because this is not impossible to include in SPH, but of course, if you just have a bare SPH solver, putting a ray tracing based solver on top of that would be extra work. Maybe we do it in the future, but currently we don't have it. But what the equations that I showed you already model is, of course, conduction and convection, conduction within the fluid and convection of the fluid due to the fluid motion. And a test case that we used there is a jet on plate case. This is from the electric engine industry, where people have coolant oil that is spilled on coil windings in electric engines. They heat up due to the electric engine producing heat. And people want to develop new cooling concepts for those, which is why they request the help of CFD codes. And of course, SPH is a good method here because it's a free surface flow. So the merits of the SPH method should be well suited for an application like that. And here, American researchers did a very simple test where they had like a coolant jet on a plate. The plate had different surfaces with this rippled contour, and then they measured out the heat transfer coefficient of these. And we used that to set up a simulation with the exact same geometric properties and fluid properties. And then check like, okay, what is the temperature distribution in the jet? And based on that, we derive what is the heat transfer into the fluid, like what is the cooling effect? And then basically you can do all the studies that you would love to do. For instance, resolution studies where you see like, okay, how does my predicted heat transfer coefficient change with particle resolution for various velocities of the impingement jet. And as you would expect, for low velocities, you get it quite easily. The higher the velocity is, the finer the resolution is that is necessary to capture these values correctly. Of course, we are not only restrained to simple tests like that. So another test case that I also would like to hint you to is a full-scale, or not full-scale, but laboratory-scale electric engine. This is a French group. They run experiments on that and measured the heat transfer coefficient there as well. And they provided the geometric data. So we also use that as a benchmark, set up a model. Basically, what the task is that of the various coils, there are 12 coil windings. You want to find the heat transfer coefficient individually. There are 5 inlets spilling the coolant oil on the coils. And wait, let's have a look on the simulation itself. So this is then the simulation. oil enters from above. Here, the shaft is spinning with a very high rotational speed, and you see like how the oil is heating up, the coolant oil is heating up, and based on that, you can compute the heat transfer coefficient, which we did. So this plot shows the heat transfer coefficient for the various coils. It's a cumulative plot, so the various colors correspond to the color-coded coils up there, and we've been able to find a match with the experiment up to 80%, which is quite good. Still, there's some work to be done, and as this is a scientific audience here, this is, for instance, something where we think that the scientific community could put some research effort into it to increase the accuracy of models like that even further. Then this is our latest development, non-Newtonian fluids. I already mentioned it, and this was no joke. We've been approached by a company that is tasked with building machines to package chocolate. And typically in these pumps, you have a flow of molten chocolate. And the first time you hear about it, you think like, okay, that's fun. I want to have some chocolate. But then you realize from an engineering perspective, this is an extremely intricate task because chocolate is a shear thinning fluid, meaning it's having a non-Newtonian behavior. Its viscosity is changing as a function of the shear rate. And so when you delve into these non-Newtonian models, you see that there is a lot that you can do, and there is a plethora of various models. As soon as it's non-Newtonian, you could say like, hey, maybe it's shear rate dependent. Then maybe you would go to a power law. There are also viscoelastic models, like for the enthusiasts among you, Aldroyd 8 family is the buzzword there. Google it if you are interested in these. And of course, there are elastic yield models, basically modeling a Hookean law into your fluid behavior. I personally am not so sure whether it's then still fine to call it a fluid, but yeah, for completeness, let's say it's there. The key point is that all of these change the deviatoric stress tensor in your momentum equation. So this is something that you need to implement into your SPH code. And there are a few challenges coming with that. So the main challenge is that there is no one-fits-it-all model. Each type of modeling approach has certain rheological phenomena that it can and cannot capture. So you have to choose like, okay, which model do I want to have? This is also a practical question when you build commercial codes, because in the end, the user will be tasked with choosing a model, and often the users are not experts in fluid dynamics. So you have to guide them a bit like in their choice. The main aspect that you want to be good at is the model should capture phenomena that are relevant for the industry. Data should be available, which is often a big deal. It should be simple to be handled by the user. And of course, you need good validation cases. And what we chose at Dive is that we said like, okay, we go for a very straightforward model where we model the viscosity as a function of the shear rate. And this is provided to our code as simple CSV files. Why do we think that this is how you should do it when you build a practical SPH code? And I really would recommend this also to you guys with your academic codes, because if it's just a CSV table from which you interpolate data, you can put in any model. You are not restricted to a certain power law or whatsoever. You just need a data table and interpolate from that. Of course, getting that data might be a problem, but this is what you can do. And then you have quite flexible solvers at your hand. Like you can model pseudo-Bingham fluids in other nice materials. Okay, so we also validated this one, and a validation case that we use is a lid-driven cavity flow with shear thinning behavior. You find it in this publication by the Journal of Engineering Analysis with Boundary Elements. What these people did, it is a 2D case where they had a lid-driven cavity and they filled it with a non-Newtonian fluid. We extended it to 3D because our solver is 3D. And then we basically checked like velocity profiles at certain reference positions, which is a very good benchmark that we also would recommend to any other person that is benchmarking non-Newtonian fluids in SPH or any CFD code actually. And we also compared it to viscosity profiles at the same locations, and we see a good match. Of course, we're not only doing academic research, we try to also see like, can we model real world phenomena? And something that we looked at was, can we model a ketchup bottle? And the first thing that you have is, of course, what are the properties of ketchup? There is, which I found quite funny, a publication on this in the Slovakian Journal of Food Science, where you find all the rheological properties of tomato ketchup. We use this then to run a ketchup simulation, which you see there. And interestingly, like, of course, this is, I think, for an audience like you, more interesting. You can then see in this cross-sectional view the different viscosities. They change as a function of the shear rate. This is what also the users are interested in when they design pumps to pump ketchup, chocolate, or whatsoever. They want to see like, where are the shear rates high, where could it be that food gets stuck, stuff like that. So now I'm coming to the end of my talk. The question is, what next? Like, you have complex materials, you can model surface tension, thermal behavior, non-Newtonian fluids. And then, of course, you start looking into more complex industrial applications. An application like this, if you remember, this was the one on my title slide. And this is a mixer mixing a fluid. And what's interesting is once you did all the effort in developing these models, you realize, hey, I have a transport equation, and it was initially meant to model thermal behavior and how it interacts with the viscosity. But as it's a transport equation, who says that this color coding is temperature? What you see here, actually, it's mixture fraction. So you use the parabolic equation that you already implemented, developed, and tested for thermal modeling to also model other effects like diffusion. This is really something that you get for free in the end once you did all that. Coming to my conclusions, modeling capillary flow due to surface tension is a good application for SPH, especially because it's free surface and all of that. Thermal models in SPH are straightforward. And non-Newtonian fluid models are now becoming one center of industrial SPH research. I'm emphasizing this because I think here we are not at the end of the line. There's still a lot that we can do. And I would like to encourage you to have a look into that and publish as much as you can. Thanks for your attention.
Thank you very much, Georg. So now we, as our usual case, we will finish all the presentation and then ask question together. So we will go to the second question. Presentation will be presented by Andreas Baumann from University of Stuttgart, and his presentation is investigation of deep hole drilling with mesh-free SPH simulation methods. So Andreas, please.
All right, thank you for having me. Just let me share my screen shortly. You should be able to see my slides now.
Yes.
All right, great. Okay, from one application, I come directly to a second one. We are looking into the modeling of deep hole drilling. That's a specific drilling process which is applied in certain industries, like for medical applications, like medical devices, also in automotive industries and so on. It's a bit more complex than normal drilling, so that's why it becomes interesting for us to perform computer-driven or simulation-based experiments to actually save us experimental time and thereby saving money in the end, which is always the interest for the industry. Just to give you an understanding, what is deep drilling actually in total? What you all remember probably is a twisted drill, which we all have probably used at home to drill holes into a wall. It has two cutting edges, and it's a fairly simple drill. It rotates, and thereby the chips are evacuated through the fluids out of it. You can support the whole process by adding additional cooling channels, which through you pump some cooling liquid, which adds as lubricant, but also as a cooling liquid to keep the temperatures reasonable at the cutting edge and to decrease the wear. However, this drill has some not so advantageous compared to a single lip drill, which has originally been developed to drill guns. That's why it's also called gun drilling in English. It has a single cutting edge, and thereby this asymmetric cutting edge leads to a constant deflection due to the cutting forces of the drill head. And thereby the back side of the drill is constantly burnishing over the borehole, and thereby leading to a high quality of the borehole. We have basically constantly burnishing process of the borehole. Furthermore, due to its features, it has a high straightness of the borehole, and it requires basically this cooling liquid way more than a twisted drill. We don't have any helical lead fluid, which would already remove the chips from the borehole, and thereby we are completely relying on the cutting fluid. To give you an example of that, I have two simulations. On the left-hand side, I have two views on the same twisted drill. One of these fluid is later filled with or flushed with cutting fluid to remove the chips, and the other ones removes the chips out of the borehole completely dry. On the right-hand side, I have 2 times the single lip drill, one without any cooling liquid and one with the cooling liquid. And we see in comparison that for the twisted drill, the chips are removed nevertheless if you have cooling liquid or not. Of course, by adding the additional cooling liquid, it gets much more faster and thereby more reliable in the process. However, for the single lip drill, we are relying heavily on the cutting fluid to remove the chips as they don't move quite that much out of the borehole, more or less just by the afterwards coming chips at the end, pushing them out of the borehole. And why is this actually a problem? I already talked about deep hole drilling. So what is deep hole drilling in general? Deep hole drilling refers to deep boreholes which are 10 times the diameter in the depth, so quite actually deep. And also compared to drilling holes at home, usually when we drill a hole into a wall or so, or even with an industry drill for machining metal parts, we regularly remove the drill out of the borehole and then we push it back in to continue drilling. However, for high performance applications and in deeper drilling, we cannot remove the drill out of the borehole to remove the chips out of it, due to that it leads to less straight boreholes and also reduces the quality of the borehole. That's why we also keep drilling straight forward and we rely on the cutting fluid to remove the chips. These drills come in all shapes. They can be up to several meters in length, and we are looking at the moment as only a diameter of 2 millimeters. So it has a quite a wide range of applications, based on, of course, also the dimensions of the drill. What is on aspect we are looking into especially, or at least my thesis is going into the direction, that's the chip jamming. One specific problem of single lip deep hole drilling is when a chip is removed and it gets stuck, so for example, between the drill shank and the borehole, it blocks the complete evacuation of the oncoming chips. This leads to a problematic behavior. First of all, this chips constantly rubbing over the borehole, leading to a wear of the drill hole. And also it can lead marks and blocks further chips from its evacuation. It requires an increased drill torque to continue drilling. However, until a certain point, when you no longer can increase your required drill torque, the drills just snap steadily because the tool strength is exceeded. And once the drill has snapped, the complete workpiece becomes garbage and you have to start from the beginning. Such chip jamming can occur, for example, when you have a degree increasing wear of the cutting edge and thereby coming on different chip forms than you have anticipated in your drill parameters, and thereby your process is no longer as reliable as you would like to have it. And this is a problem. So our interest is in modeling this phenomena and also the complete process to improve the drill design, to increase the reliability, and thereby for industry, of course, reducing the tool lifetime and decreasing costs in the end. That's what it's all about. So just to give you a short view about the model, I don't want to talk about SPH in general because it's a SPH group meeting, so you're all familiar with the equations. We apply a combined SPH DM simulation. So we have SPH for the cutting fluid, and we apply DM as a discrete element method for the chips, the borehole, and the drill. At the moment, that's for our rigid application. I'm later going to talk also about our current research into adding flexibility to the chips. We are coupling DM and SPH by a repulsive force interaction, which prevents that the particles go through the wall and lead to the buoyancy of the correct chips. We did some validation of our simulation model. As you imagine, our drill only has 2 millimeters in diameter, and it's quite hard to get some experimental data from this process, as we are quite limited in how we can apply some sensors and get some views. With our partners at the TU Dortmund, we were able to do some visual studies of this simulation of the drill. So for these analysis, we keep the drill static and we rotate the borehole instead. And thereby we have a plexiglass cylinder which we can look through, and thereby we can see a constantly on the cutting edge and see how the chips are forming. And for this simulation, or for this comparison, better said, we added some image, some particles to track through the camera image. Don't get confused, they are also called particles. They have nothing in common with the SPH particles. However, we can track them, and for our setup with, let's say, a pressure of 100 bar, we were able to measure a certain velocity along the outer circumference of the cutting liquid. And by comparing this data together with a finite volume method and also with our assimilation of in SPH, we agreed, we had a good, quite a good agreement between the experimental data and the simulation data. So we are all within the same ballpark range, which gives us quite a confidence that our model is quite good. So now we have a base model. We are somewhat sure that it gives us a good prediction. So now we want to apply it to improve the drill. For example, we have this reference drill here in the top view, and we also have a modified drill. For this modified drill, we did some finite element analysis and also some design choices. So for example, we changed the cutting edge at the front of this. We know that by changing the cutting edge, we get a different size and shape of the chips. And also by applying the finite elements, we were able to increase the diameter or the cross-section of the cooling channel, which allows us to pump more cooling liquid into the front of the borehole and thereby increasing the cutting fluid flow. And by comparison of these two simulations, we see that the chips are now much more faster removed from the borehole, and this gives us a higher reliability of the process. I haven't talked yet about how we actually add the chips to the simulations. We have chosen quite a simple approach to add our chips to the simulation. We don't actually perform any chip forming simulation because this is quite computationally expensive and would furthermore would also quite prolong the simulation as it already is. So we have chips, we take them from the experimental experiments we have, we digitize them, we clean them up to get a clean STL format, and then we add them at the moment as rigid bodies from the beginning. We try to place them close as possible to the cutting edge as they would come in reality from the simulation process. And then we introduce them into the borehole, and once they are completely within the borehole, we set them free, and then they are governed by their equations of motion, the interaction with the fluid, and then we have the regular simulation and evacuation of the chips. So on the right-hand side, we have a plot of the positions of the chips. So in dashed, we see the modified chips along over time, which we add. And in straight lines, we have the chips of the standard model or the reference drill. And we see by the slope of these positions over time that the modified drill evacuates the chips much more faster than for the standard drill, and thereby we increase the reliability that chips are actually removed and don't get stuck at the bottom. So what we already have shown is that the simple drill modifications lead to a changed chip form. We have an improved flow, and thereby, of course, we get a faster chip evacuation, which is helpful in the end. So also, now we have removed the chips. Now we can also look at the cutting liquid and the cooling properties of it. So if we look at the simulation from below, we see that actually behind the cutting edge, so in this area here, we have the outlet of the cross-section of the cutting fluid flow. So, but however, behind the cutting edge, we have almost no fluid motion. This leads to the behavior that actually any heat which is generated by the cutting edge and is in this area is not very well transported out of the borehole. So we have not a sufficient cooling effect behind the cutting edge, which thereby, of course, leads to increased wear of the borehole. So our idea was, okay, let's add a second fluid behind the cutting edge, which allows the fluid to divert around the cutting edge, thereby cooling the cutting edge more efficiently, and then getting out of the borehole through a second fluid. We did some tests with different designs. So we have the reference up here. We see also when the streamlines, we have not much flow behind the cutting edge. We added a slight second fluid on the right-hand side. It becomes a bit better, but not much. And by adding a quite severe cut about the tool, we get a bit better flow. However, in the end, we are limited in the design based on the machinability of these fluids. So we need to add them posterior to the machining process, and also by the structural strengths of the drill. We cannot remove that much material out here before the drill becomes just too weak and just snaps also. So we see that these minimal second fluids have only a minimal influence on the fluid flow. The main of the fluid flow still flows the regular way to remove the chips, which is, of course, one of the goals as well. However, the second flow along the cutting edge is not sufficient to improve the cooling of the cutting edge significantly. It would require a significantly larger drainage along this way to increase this furthermore. However, it comes back that the structural strength wouldn't then be guaranteed. Now I talked about a bit how we apply that to actually improve the design of the models. The next step is we want to investigate this phenomenon of chip jamming in the process. So we tried first of all to replace the rigid chips by an SPH solid application of the chips. So we apply SPH also to model the solid equations of motions for continua for this chip. So we placed also some SPH particles here, and we added an artificial barrier right at the end to get a first modeling of our chip jamming. This barrier only blocks the chip from extrudation, however, it's permeable for the fluid. This is similar to a small chip which is stuck here, which is somewhat flexible to allow the fluid to pass, however, blocks all oncoming chips in the evacuation. Okay. Let's compare that to our previous simulations to know, okay, what we did before was good or not. On the right-hand side, I also added again the reference to our simulation of the rigid chips in the evacuation process. And here below, I have the simulation with the flexible chips. On the left-hand side, I have an overlay of the chip in its position. So we have no translational motion. On the right-hand side, we just overlaid just to get the elastic deformation of the chip itself. On the right-hand side, you see the simulation from before. We have the elastic chip before placed here within the evacuation fluid, and we have the fluid flow coming from the bottom, and of course, our artificial barrier on the right. And we see that the fluid flow catches the chip, transports it along, and also by looking onto this elastic deformation, we see that once the chip is catched by the fluid flow, we don't see much deformation of the chip itself. So it's quite more or less rigid. So we can conclude that we have no major deformation. So our earlier approach to apply for solely the chip evacuation, rigid chips, is sufficient enough. So this is a good approach. So let's talk about the collision with the chip barrier. So we have that the chip flows along the fluid flow, with the fluid flow along the fluid, and it hits the barrier. And we see in this video that once it hits the barrier, we have a quite major oscillation of the chip. It's like hitting it with a hammer. So we have I'm looking for the word right now. However, we have quite rigid, quite significant deformation on impact of chips. However, what you also see, we applied first of all a fully elastic material model onto our chip, and we see after the collision with the wall, the chip retracts immediately in its original form. So we see first of all, okay, once the chip hits the wall, the elastic model becomes essential. This phenomena can no longer be described by a rigid model. And also we see furthermore that the elastic model itself isn't enough. We need also to introduce plastic formulations, as we would assume from the videos we know that once the chip is hitting the wall, we have a plastic deformation of the chip. It's not that fully elastic like it's here modeled in the simulation. And also it would be probably deforming under the fluid pressure. So, all right, I have some updated slides about that. We then added a perfect plastic material model for another simulation where we did the same. No, it's not starting the videos. Okay, let me start them manually. And we see that the elastic deformation becomes much more, way decreased by applying the plastic material model. And we also see in the simulations that we start to get a plastic deformation of the chips once it hits the wall and the fluid pressure increases. And that's actually what we wanted to see. This simulation is currently still running, so I have to postpone a bit more of the results for a future presentation. However, we are quite looking forward to get more insight about this process. We're also trying to apply different plasticity models to see what is actually a good fit for the phenomenon we are seeing. The second thing I want to talk about is the fluid flow itself. I think in general, a good rule of thumb for the weakly compressible sound velocity is to apply 10 times the maximum velocity we see in the simulation. We did this in one of the first simulations. However, we thereby have a density increase of more than 10% in some places. more than 1%, which thereby exceeds the assumption of our weakly compressible formulation. So we also need to change that to also adapt for a higher sound velocity, which of course thereby comes with a higher computational times. And I added the second simulation here. We see no longer that density increase as the fluid now is not as weakly compressible as before. However, we are much closer to the reality now. So I already showed you the first approach about this flexible modeling with SPH particles. We have seen some problems like that we get some random oscillations. We have some high oscillations of the chip deformation, which we are actually not interested. This high oscillation actually decreases the time stepping we can apply and thereby increases the simulation times we have. What we're more interested in about is the general deformation of the chips. So we're also looking into about how we can apply finite element based modeling approaches. And this is done by a floating frame of reference formulation, which we apply for the large body movements. And we superimpose the elastic deformation based on a finite element model onto this large rigid body motion. And thereby we can apply a model order reduction technique, which allows us to apply a modal reduction, which gets rid of all the high frequency oscillations of our flexible model. We only concentrate on this low frequency deformations, which are actually in interest for ourselves. So after doing the finite element meshing, we apply our model order reduction. Then we get our elastic multi-body system, which is based on the floating frame of reference. We are coupling this with a standard interface with our particle simulation in the end. And to give you a review of our current work, what is going to be in the future, we have now our finite element body here on the left, and we have our simulation here on the right. We have also coming the fluid flow from the beginning. And in the video, we see that the chip is catched quite good by the chips. However, we are currently struggling with the stability of this coupling, especially of the stability of this elastic body. And also, of course, now we are coupling two different simulation models, which increases our computational effort. So we are also looking into how we actually can increase our simulation speed to improve our simulations. Let me just shortly summarize what I have shown you today. I have talked about that deep hole drilling is a highly dynamic process. We have an initially empty borehole in our assumption. Thereby, we'll have free surfaces by the incoming cutting fluid flow. We have moving chips, which are evacuated through the chip fluid, which of course leads to moving boundaries between the cutting fluid flow and the solid chips. We saw that SPH is well suited for this investigation as it combines both free surfaces and moving boundaries in this formulation. We have seen that rigid chips are sufficient for the evocation analysis, as we see no major deformation of the chip during the chip acceleration. However, if we want to model the chip jamming in general, we need to look into flexible models. We have a deformation on impact, of course, and also we expect a further deformation by the following chips, which I haven't shown in this presentation. Also, as it is as SPH imaging, just some side notes. We see in the process evaluation that we need to increase the numeric sound diversity, and besides or going over the rule of thumb, which we usually apply depending on the conditions we have. And of course, we are always struggling with high computational times. That's all from my side. And again, thank you for having me and thank you for your attention.
Okay, thank you very much, Andreas. So now we open for questions. You can ask a question for both of the presenters on their work. And okay, please. And before that, you speak out your question. I hope you can speak your name and your affiliation, and it will be better for everyone to understand. So yeah, maybe let me speak begins. Okay, then Georgi, I would say ask you the question is when you show me the droplet falling down to the surface, there's a simulation. Do you have a free surface model for the surface tension, or you also use air and didn't show it air particles?
No, we have a free surface model. So usually in our simulations, we ignore the gas phase. This is exactly why we need a good surface tension model to capture that. Our solver would be capable of also discretizing the air with particles, but in most of the cases, we don't do it for the sake of a speed up.
So the free surface surface tension model is from the reference you showed from the PhD thesis you showed in that slide?
I would have to double check, but I think so. But I will check again. And
this is more like a thesis 2012 or 22.
Yeah,
Okay.
Bernoulli. Like this is what I meant. Like Bernoulli has a very excellent introduction of how to model surface tension. We did a few modifications, but many ideas we took from his thesis.
Okay, good. Yeah. Okay. So any other have questions?
I would have one.
Okay, good. Thank you.
I would have one to Andreas. You mentioned that you coupled your SPH solver to various other solvers, FEM and DEM. Could you elaborate a bit on how you implement that? Are these solvers that are written monolithically? Are these independent solvers that you join with some boilerplate code? You mentioned these functional mock-up. What?
Mock-up interface, exactly.
Exactly.
We do two different approaches. Our in-house code originates from a DEM solver. So we have a monolithic code which is then extended by SPH. So we have a monolithic coupling of the DEM with the SPH. We do this by also applying, as already mentioned, a repulsive force function, which then gives us the forces between the particles. The second approach, which I applied for the finite element model, was an segregated approach. We have the finite element code, which is separate from the SPH code, which is then, as you said, an Euler approach, exchanging position and forces back and forth. And therefore, we use the functional mockup interface, which is an industry standard about co-simulation, which defines some interfaces, how you can actually exchange data from one simulation to another one, and then also bundles quite nicely the finite element code, which can then be imported into our SPH simulation.
Okay. So more questions?
I have a question for Andreas, and you mentioned that you don't want to use the SPH for the solid dynamics, but I didn't catch it. Could you explain more why you didn't want to use SPH for solid dynamics?
Can you repeat the question? Apply SPH also for what?
For solid, for the structure deformation.
We do. The simulations I showed you with the first deformable chip was by applying SPH also for the solid, so for the continual equation of the deforming a solid. However, we see a high oscillation on the impact and also on the interaction with the fluid. And also, we want to check, or we want to compare it to other approaches, like finite element method, if we can then, by applying model order reductions, reduce the computational effort required for the coupling and the simulation, also by applying model auto reduction, we can get rid of this high frequency oscillations of the solid phase, and thereby hopefully also reduce our simulation times, because we are only interested about the general deformation of the chip and not this high frequency interaction which comes by the force impact.
Okay, now I understand. Thank you.
So, and the goal in the end, of course, would be to compare both of them and then to see, okay, what is actually the best approach for that. Hopefully that will be the goal of my thesis.
Okay, thank you.
Okay, more questions? Also, if you feel difficult speaking English, I can translate to you guys if anyone would like to ask. Question in Chinese is also
Professor
okay.
Hu, I have a question. I'm Xu
Okay.
Kaidong.
Mhm.
Yeah. I have a question for George. For your simulation, like mixture process, do you come across some problem like tensor instability in three-dimensional simulation, and how do you solve them?
Tensile instabilities are an issue in SPH in general. We at Dive use a special shifting technique to tackle that. If I'm not mistaken, it's the one from Lee 2021. And then, as usual, we scan the literature on this, do our tiny modifications ourselves so that the algorithms are commercially ready. But to answer your question, tensile instabilities are not a big issue in our simulation, in the simulation you just seen, just because we have a very powerful shifting technique to tackle the issue.
Oh, and will the tensor instability for Newtonian fluids will be harder for Newtonian fluids compared with Newton fluid?
This is a good question. I would not assume so. It depends on the peak viscosity that you will reach with your non-Newtonian behavior. So I would always compare the tensile instability forming in a high viscous Newtonian simulation with a simulation which is non-Newtonian but has a peak viscosity of the same range. Then I think you would run into the same level of issues when it comes to tensile instabilities. I would also like to say that one thing that we changed when we started working on these non-Newtonian fluids, and especially high viscous fluids, is our time integration scheme. So we implemented implicit steps, especially for the update of the viscosity terms, and this also helped us, getting rid of these issues.
Oh, the time steps is very small. Or the integrated scheme is very stable.
Our integration scheme is stable. Yeah,
Stable.
we have various stability conditions. Some depend on viscosity, some depend on the local velocity, and yeah, I think it's.
I see. Oh, thank you.
You're welcome.
Okay. And any other guys has also questions?
Yeah, I have a question for Andreas. You said that temperature is a problem at the tip of the drill, and you said in one simulation that you saw that there was no fluid going over the drill head or wasn't cooling it sufficiently. Did you say that just because there was not that much actual convection or fluid flow there, or did you also model the thermodynamics effect in that simulation?
At the moment, we are not modeling the thermal effects right now. We are hoping to expand our model in the future. Right now, our observation was solely based on that fluid flow and that the convection is not sufficient behind the cutting edge.
Okay, thank you.
Other questions? I have one question to Andreas. So in your case, you say the density variation could become quite high, so approaching to 10%. What is the possible physical reason there? Why you become so compressible? Or when your sound speed is low, then your density become very large. Duration very large. What's
Yeah,
possible?
the issue is mostly caused by that the chip blocks the outflow of the fluid flow, and we keep pumping fluid basically into the simulation. So thereby, of course, we are generating a quite of a closed volume where we keep adding fluid to, thereby, of course, leading to an increase of the pressure, and also when we have too compressible fluid, then also, of course, the density increases. So we need to, of course, then adjust for this changed behavior that we have now blocking outflow, and also need to decrease the compressibility, of course, to actually reflect the real behavior of the cooling liquid.
Okay, got it. Okay, thank you. Other questions? So, okay. So please. Okay, so that's if there's no more, and we thank you very much. These two presenter, Georg and Andreas, for their very good presentations. So okay, so let's thanks to two very much, and then we in the next time we will switch back to the Chinese version. So, and hopefully people feel a little more, it's not so difficult to understand. Okay, thank you very much, and let's meet next month again. Okay,
Okay.
Thank you. Bye bye.
Thank you, Georg. Thank you, Andreas.
Thank you. Bye bye.
Have a nice day. Bye bye.
Bye.